In this video, we're going to look at the distributions that are needed for the hypothesis testing. The sample statistic and the distribution form a foundation for both the hypothesis tests and the confidence intervals. The key distinction lies in the assumption about the population parameter. In hypothesis tests, we assume the population mean or proportion to be known based on the null hypothesis, while in the confidence intervals, we refrain from making such an assumption and provide an estimate with a certain level of confidence. Both methods that we use are vital tools in inferential statistics, allowing us to make informed decisions and draw meaningful conclusions about the data. So here's all of that I just said summarized here. Give you more, I would recommend you pause and read through that. A lot of reading. So when we make a claim and we want to test it, we want to make a claim about the population mean. One of the following two requirements must be met so that the central limit theorem can be applied. The sample size must be relatively large, and that means at least 30. We like more than 30, but at least 30. Or the sample appears to be normally distributed population. It's very important to verify these requirements in real life. In problems that we are usually told to assume the second condition holds if the sample size is small. So when those hold, then our choices are either a z-test or a t-test. The sample statistic, when we use a z-test. We use a z-test when the sample statistic is the sample mean of the data, x bar. If the population standard deviation is known, which is really unlikely, the distribution of the sample means will be normally distributed with that mu and the sigma divided by the square root of n, where mu is the population mean assumed in the null hypothesis. We find our z-score by doing x bar minus mu naught divided by sigma divided by the square root of n. The p-value is the tail area under the normal curve beyond x bar in the direction of the alternative hypothesis, which is the same as the tail underneath the normal distribution, standard normal distribution. That's it. Had lost my words there for a minute. Beyond z. T-test. Well, when we use a t-test is we have the sample mean x bar if the population standard deviation is not known, which is most of the time. The distribution x bar is normally distributed as above, but we use a t-distribution, so we need to know degrees of freedom, which is the number, the sample size minus 1. Since we must use s to approximate s, which is a sample deviation, to approximate sigma. The test statistic is given here, where it's s divided by n, and the p-value of the area under the t-distribution density curve beyond t in the direction of the alternative hypothesis. Now, I have something to note for a two-tailed test. The alternate hypothesis is a statement of inequality, not less or not equal to. The p-value is a tail outside of either statistic doubled, which is the probability of getting the outcome in its extreme in either direction. So, what about when you have a proportion? Well, when you're testing about a proportion, it's a binomial distribution. You have a specified number of independent trials. Each trial has two outcomes, either success or failure. Plus, we require n times p to be greater than or equal to 5. At the same time, n times q, that should be n times q, is greater than or equal to 5. So that the binomial distribution has a nice bell shape and can be approximated by a normal distribution. We do the probability or proportion, the proportion z-test. This test, the sample statistic is a sample proportion, and we use p prime or p hat, which is x over n. It is going to be normally distributed, where we have p naught, the square root of p naught q naught over n, and the sample proportion assumed to be p prime minus p naught, square root of p naught q naught over n. The p-value of the tail under the density curve p prime beyond the sample statistic p prime in the direction of the null hypothesis, which is the same as the tail area under the standard normal density curve, where we're using the standard normal distribution. beyond the test statistic Z. So determine which distribution you should be using to form the hypothesis test. A sample mean is 13. The sample mean, population mean is 13, excuse me. The sample mean is 12.8. The sample standard deviation is 2. The sample size is 20. Assume the underlying population is normal. Because it doesn't say anything about the population standard deviation, then this is a t-distribution. And sample size is 20, so the degrees of freedom is 19. Population has a mean of 25 and a standard deviation of 5. So we know right out of the way this is a normal distribution. So the normal distribution, X is approximately a normal distribution with a mean, sample mean of 24, and the sigma, which is 5, divided by the square root of 108. It is thought that 42% of the respondents in a taste test would prefer brand A. In a particular test of 100 people, 39% preferred brand A. So this is a proportion. So we're going to have P hat, or P prime is approximately normal with a 0.39. That's the preferred brand, with the square root of 0.39, 1 minus 0.39, and then divided by my n, which is 100 people. That's it for this video.